Consider a thin rectangular panel loaded as shown in figure 3.28. What we need to do is show that the Airy stress function, phi here, solves the problem, and we also need to find the constants C1, C2, and C3. So now, with the Airy stress function, since it is a second order function, that will automatically satisfy the compatibility equation, where the gradient squared times the gradient squared of phi is equal to 0. So we can indeed use this to solve the problem. So now, in terms of finding the constants C1, C2, and C3, what we can start out by doing is writing the relation between sigma x, sigma y, and tau xy. So for sigma x, we can find this by taking the second partial derivative of phi with respect to y, and that will give us 2 times c3. And for sigma y, we can take the second partial derivative of phi with respect to x, and that will give 2 times c1. And then for tau xy, we can take the negative second partial derivative of phi with respect to x and with respect to y as well. And that'll give negative c2. So now, there are many, many different possible answers to this problem, but in order to actually solve them, we have to check our boundary conditions to find out what our values C1, C2, and C3 actually are. So next we will check the boundary conditions. So we can check two of these conditions, one on the face here where x is equal to a divided by 2, and then we can also check this face up here where y is equal to b divided by 2. Now if you wanted to, you could also check x is equal to negative a divided by 2 or y is equal to negative b divided by 2. But for this, I'm going to start out by saying at x is equal to a divided by 2, the normal vector is going to be 1, 0. And the reason for this is because this face points purely in the x direction. There is no y component. So essentially just have that x component there, essentially 1 and then 0 because there is no y component. And then also for our traction vector, that is going to be equal to sigma naught 0. And the reason it's going to be equal to sigma naught 0 is because there is a stress acting on that face in the x direction, and this stress is sigma naught. Now there are also no y direction stresses or y direction components, so that's why we have a 0 here for the y component. And now what we can do next is we can use Cauchy's equation, where we have some stress field times our normal vector, 1, 0, and that's going to equal our traction vector, which in this case is sigma naught 0. Now, this essentially stress field, you can write that above here as sigma. That is going to be equal to sigma x, tau xy, sigma y. So we can use our values that we calculated before to get a stress field of 2c3 minus c2 minus c2 and 2c1. So we can use that below here. So again, we have 2c3 minus c2 minus c2 and 2c1. And by solving this, on the bottom, we get that c2 is equal to 0. And this first row, by solving it, we get that 2c3 is equal to sigma naught. So by dividing by 2, we get that c3 is equal to sigma naught divided by 2. So now let's check the boundary when y is equal to b divided by 2. So now we can say at y is equal to b divided by 2, we'll say that the normal vector is going to be equal to 0, 1. And the reason for this is because this face points purely in the y direction for the normal component. There is no x component. And now we also notice we have no stresses acting on this face in the x direction or the y direction. So in this case, what we'll say is the traction vector will be equal to 0. So now we can write a similar format for Cauchy's equation as before. So we have the 2c3 minus c2 minus c2 and 2c1. Then we'll write the normal vector, 5, 0, 1, and then we'll set that equal to the traction vector, which is 0, 0. So with the top row, we get that c2 is equal to 0. And with the bottom row, we get that c1 is equal to 0. So we can conclude that c1 is equal to c2 equal to 0, and c3 is equal to sigma naught divided by 2. So now we have all of our coefficients for the Airy stress function.